Hello and welcome to the module on standard deviation, correlation and linear regression. By the end of this module, you would have learnt the basic concepts of standard deviation, correlation and regression, how to find the strength of association between two variables through a correlation coefficient, and how to find the line of best fit using the least square regression line. Let us now see the measures of central tendency and dispersion. The mean, median and the mode give us only one characteristic of a frequency distribution, that is the central tendency. These averages do not tell us anything about how the scores of measurements are arranged in relation to the center. To give a better picture of a distribution, we also need to know the extent to which the individual values deviate or scatter from the central tendency. Measures of dispersion help us to know the degree of uniformity and consistency in the data series. Let us begin with standard deviation. The concept of standard deviation was introduced by Pearson in 1893. It is so far the most widely used measure to study dispersion. It is also known as the root mean square deviation and is denoted by the Greek alphabet sigma. The greater the amount of variability, the greater is the standard deviation. A small standard deviation means a high degree of homogeneity in the series. Standard deviation is also useful in judging the representativeness of the mean. What is the relation between standard deviation and normal curve? The standard deviation, as we all know, is a statistic that tells us how tightly all the values are clustered around the mean in the data. When the observations are very close to each other and the bell-shaped curve is steep, the standard deviation is small, denoted by the blue curve. When the observations are spread apart and the bell curve is relatively flat, that tells you that you have a relatively larger spread or a higher standard deviation, denoted by the green curve. The bell curve, which represents a normal distribution of the data, shows what the standard deviation represents. One standard deviation away from the mean, that is mu, in either of the directions on the horizontal axis accounts for around 68% of the data. Two standard deviations away from the mean accounts for roughly 95% of the data, while three standard deviations represent about 99.76% of the data values. The standard deviation formula can be represented using the sigma notation. It can be stated as sigma is equal to under root summation x minus mu bracket square upon the total number of values, that is n. Note that the standard deviation is the square root of the variance. Now let us see the difference between population standard deviation and sample standard deviation. The population standard deviation is used when the data being analyzed includes the entire set of possible data values. It is usually given by the formula sigma x equal to under root summation xi minus x bar bracket square upon n, where n is the total number of units in the population. When we come to the sample standard deviation, the sample values are used to calculate the standard deviation instead of the population values. The sample standard deviation is usually denoted by Sx and is given as under root summation xi minus x bar bracket square divided by n minus 1. For example, if all the students in a college were asked how many books they had borrowed in the last academic year, then it would imply that the entire population has been studied. If this was the case, then population standard deviation should be used. However, if only a few students were asked about their borrowing of books, then one should use the sample standard deviation formula. An example on how to compute the standard deviation using this formula has been given in quadrant 1. Let us now come to coefficient of variation. which is usually abbreviated as C dot V. The standard deviation discussed above is an absolute measure of variation. If we want to compare the variability of two or more series, we use the corresponding measure known as the coefficient of variation. That group or series for which the coefficient of variation is greater is said to be more variable, in other words less consistent and less stable. Since sigma, that is the standard deviation, and x bar, which is the mean, are both measured in the same units, the coefficient of variation becomes a pure number independent of the unit of measurement. It can thus be used for comparing the dispersion of two or more distributions given in different units. The formula for coefficient of variation is given as CV equal to sigma upon x bar into 100. Now let us see what correlation means. Correlation is a statistical technique used for analyzing the behavior of two or more variables. The relationship between any two variables or their interdependence is known as correlation. It is also described as covariation among the two variables or ranks in the same or reverse direction. It examines and derives the degree and direction of relationships. Given any two variables, say x and y, we often wish to know what will happen to one of these variables if some changes take place in the other. It is important for us to remember that correlation does not necessarily indicate a cause and effect relationship. It only provides us with a pure quantitative measure. Let us now see how correlation can be used in practical life. The study of correlation is of immense use in our day-to-day life because most of the variables show some kind of relationship. For example, there is always a relationship between price and supply. With the help of correlation analysis, we can measure the degree of relationship existing between these two variables. Once we know that the two variables are related, we can go ahead and estimate the value of one variable given the value of the other. This is done with the help of regression analysis. In business, correlation enables the executive to estimate the costs, sales, prices and other variables on the basis of some other series with which these may be functionally related. There are four main types of correlation. First, positive and negative. Second, simple and multiple. Third, partial and total. And the fourth one, linear and non-linear. Positive correlation refers to the movement of variables in the same direction. It is simply the increase in the value of one variable accompanied by the increase in the value of the other. Negative or inverse correlation, on the other hand, refers to the movement of the variables in the opposite direction. Simple correlation refers to the relationship between two variables, one dependent and one independent, while multiple correlation refers to the relationship between more than two variables, that is one dependent and several independent variables. For example, if we study the relationship between price of steel, the price of cars and the price of tires, it is a problem of multiple correlation. Under partial correlation, we assume only two variables to be influencing each other, keeping the effect of the other influencing variables constant, whereas in total correlation, no variables are held constant. For example, we study the effect of price of a good on demand for that good, keeping income levels constant. The fourth, the linear and the non-linear type, is based on the ratio of change between the variables under consideration. A linear correlation has a constant ratio of variation in the values of two variables, whereas in non-linear or curvilinear correlation, the amount of change in one variable does not bear a constant ratio to the amount of change in the other related variable. For example, if we double the hours of study, the marks would not necessarily be doubled, or if the amount of rainfall were to double, the production of food grains would not necessarily be doubled. Let us now come to the coefficient of correlation. The degree of correlation is measured by the coefficient of correlation for any amount of change in the concerned variables. This coefficient usually ranges between -1 and +1. The broad categories of classification can be given as: if the degree is perfect, the direction is positive, then the correlation would be +1. If the direction is negative, the value would be -1. If the degree is significant and the direction is positive, the correlation would range from +0.75 to +1, and if it is negative, it would range from -0.75 to -1. In case of high degree of correlation and positive direction, the correlation coefficient value would range from +0.50 to +0.75, whereas in case of negative direction, it would go from -0.50 to -0.75. For low or medium degree of association and positive direction, the value would range from +0.25 to +0.50, and in case of negative, it would be -0.25 to -0.50. If the correlation is very insignificant or small, the value in case of positive direction would usually be either 0 or 0 to +0.25. In case of negative direction, it would be 0 to -0.25. If there is no correlation between the two variables, that is, the correlation is absent, whether it is positive or negative, the values would be nothing but 0. We can study the correlation between two sets of values or figures through the following methods. First, by drawing the graph of that data. Second, by constructing a scatter diagram. And third, by calculating the coefficient of correlation. In graphical method, each of the two sets of figures are plotted on the graph, and then these points are connected. If the two curves move in the same direction, then the correlation between them is positive, whereas if the two curves move in the opposite direction, then it is obvious that the correlation is negative. Scatter diagram is the simplest device for asserting whether the two variables are related. By looking at the scatter of various points, we can form an idea as to whether the variables are related or not. The greater the scatter plotted on the chart, the lesser is the relationship between the two variables. If the points are on a straight line falling from upper left hand corner to lower right hand corner, the correlation is said to be perfectly negative. If, on the other hand, the points are rising from the lower left hand corner to the upper right hand corner, we have the case of perfect positive correlation. If the plotted points fall in a narrow band, there would be a high degree of correlation between them. Correlation would be positive if these points show a rising tendency, again from lower left hand corner to upper right hand corner, as depicted in figure A. And correlation would be negative if the points show a declining tendency from upper left hand corner to the lower right hand corner, as shown in figure B. On the other hand, if the points are widely scattered all over the diagram in a haphazard manner, it is an indication of the absence of any relationship between the variables, which can be very well seen in figure C. Let us come to understand the Pearson's correlation coefficient. This coefficient is also known as Pearson's product moment correlation coefficient. Correlation, as we have seen, is a technique for investigating the relationship between two quantitative continuous variables, for example, age and blood pressure. Pearson's correlation coefficient, denoted by the alphabet R, is a measure of the strength of association between the two variables. The first step in studying the relationship between the two variables is to draw a scatter plot to check whether there is any form of linearity between them or not. Then we go ahead and calculate the correlation coefficient. The formula for calculating the correlation coefficient can be given as R equal to summation x minus x bar into y minus y bar divided by under root summation x minus x bar bracket square into summation y minus y bar bracket square. This can be further simplified as R equal to summation xy upon n into sigma x and sigma y, where sigma x and sigma y are the corresponding standard deviations for the series x and y respectively, and x and y are the differences of the values from their respective means. N, as we all know, are the number of observations in your data. Please refer to the quadrant 1 for an example on Pearson's correlation coefficient. Let us now see the merits and the limitations of the Pearson's coefficient of correlation. Amongst all the methods used for measuring the degree of relationship, Pearson's method is the most popular. However, the utility of this coefficient depends in part on a wide knowledge of the meaning of this yardstick together with its limitations. These include: first, the correlation relationship always assumes a linear relationship regardless of the fact whether the assumption is correct or not. The second limitation is that we need to take great care in interpreting the value of this coefficient. The value is unduly affected by extreme items. Moreover, as compared with the other methods, this method takes more time to compute. Let us see what a correlation does not tell you. The evidence from the correlation does not allow one to make cause and effect judgments. That is, we cannot say that father's height caused son's height to be smaller or bigger. Likewise, we cannot say that watching violence on TV causes one to act more violently. It might be that more violent individuals choose to watch more violence on TV. We just do not know the answer. The correlation statistic does not address such issues. How to interpret the value of the coefficient? As the reliability of the estimates depend on the closeness of the relationship, it is imperative that utmost care be taken while interpreting the value of the correlation. Otherwise, incorrect conclusions may be drawn. The following general rules are observed to interpret the value of R. When R is plus 1, means there is perfect positive relationship between the variables. When R is minus 1, it means there is perfect negative relationship between the variables. When R is 0, it means there is no relationship between the variables. The closer R is to either plus 1 or minus 1, the more stronger is the relationship between the variables. Let us see what is rank correlation coefficient. Carl Pearson's method of estimation the correlation coefficient is based on the assumption that the population under study is normally distributed. When it is known to us that the distribution is not normal, we need a measure of correlation that involves no such assumption. Moreover, there are many areas where it is not possible to measure the variability under consideration quantitatively. Both these issues can be addressed by ranking the observations according to the size and basing the calculations on their ranks rather than on the original observations. This measure is used especially when quantitative measures for certain factors cannot be fixed, but the individuals in the groups can be arranged in order, thereby obtaining a number known as rank for each individual in the group. The rank correlation is usually denoted by the Greek alphabet rho and is defined as rho equal to 1 minus 6 summation d square upon n into bracket n square minus 1, where d is the difference between the ranks of the two series. Please refer to quadrant 1 for an example on rank correlation coefficient. Let us see the merits and demerits of the rank correlation method. The merits: this method is simple to understand and easier to apply than the Pearson's method. In case the data is of qualitative nature like efficiency, intelligence, etc., this method can be used with great advantage. Moreover, this is the only method that can be used when we are given the ranks and not the actual data. We also have a few limitations for this method. This method cannot be used for finding out correlation in a grouped frequency distribution. Also, it is difficult to implement or use this method if the number of items in your data exceeds 30. In case of repeated ranks, the formula for the coefficient of correlation through this method has to be modified and used. The illustration can be found in quadrant 1. Let us see the concept of linear regression. The term regression was first introduced by Sir Francis Galton in 1877 while studying the relationship between height of fathers and sons. Regression is a branch of statistical theory that is widely used in all the scientific disciplines. Regression analysis is used majorly for two things. First, predict the value of the dependent variable based on the value of at least one independent variable. Second, explain the impact of changes in the independent variable on the dependent variable. Remember, there is a difference between regression and correlation. The correlation coefficient is a measure of degree of covariance between the two variables x and y, whereas the main objective of regression is to study the nature of relationship between the variables so that we are able to predict the value of one on the basis of another. In regression analysis, the cause and effect relationship is clearly indicated. One variable is taken as dependent while the other as independent. The variable whose value is influenced is the dependent variable, and the variable that exerts this influence is the independent variable. The independent variable is also called as the explanatory variable. What is a simple linear regression model? This is a model in which there is only one independent variable. The relationship between two variables x and y is described by a linear function. Two variables are said to have a linear relationship when change in the independent variable, say y, by 1 unit leads to a constant absolute change in the dependent variable, say x. When we plot the variables on a scatter diagram and draw the two lines of best fit which pass through these plotted points, the two lines are called as regression lines. In case of linear regression, these lines are straight lines. If we take the case of two variables x and y, we have two regression lines as the regression line of x on y and the regression line of y on x. The regression line of y on x gives us the most probable value for y for a given value of x, whereas the regression line of x on y gives us the most probable value of x for a given value of y. However, when there is perfect positive or perfect negative correlation, the two regression lines will coincide. That is, in that case, we will have only one line. the farther the regression lines from each other, the lesser is the degree of correlation between them. If the variables are independent, R is 0, then the two lines are at right angles to each other. Let us see how the regression equation of y on x looks like. This line of regression is usually expressed as y equal to a plus bx. In the above equation, a and b are both constants. These are determined by the positioning of the line. These constants are called as the parameters of that line. The parameter a determines the distance of the line directly above or below the origin, whereas parameter b determines the slope of the line fitted. The values of a and b are obtained by the method of least squares. According to this method, the line should be drawn through the plotted points in such a way that the sum of squares of deviations of the actual y values from the computed y values is the least or the minimum. Such a line is known as the line of best fit. A similar derivation can be used to explain the regression of x on y. What is the standard error of estimate concept? Perfect prediction is not always possible with the help of regression equations. So, we need a measure on how precise this prediction can be. The standard error of estimate, symbolized by SXY, measures the dispersion about the regression line. In other words, the standard error measures the accuracy of the estimated figures. The smaller the value of the standard error of estimate, the closer will be the dots to the regression line, and better will be the estimates based on the equation for this line. Every sample has some variation in it, unless all the values are identical, and that is unlikely to happen. The total variation is made of two parts: the part that can be explained by the regression equation and the part that cannot be explained by the regression equation. The ratio of the explained variation to the total variation is nothing but the standard error. Let us summarize the entire module. Measure of dispersion helps us to know the scatter from the central tendency. Standard deviation is so far the most widely used measure to study dispersion. The greater the amount of variability, greater is the standard deviation. If we want to compare the variability of two or more series, we use the coefficient of variation. That group or series for which the coefficient of variation is greater is said to be more variable or less consistent and less stable. It is important for us to remember that correlation does not necessarily indicate a cause and effect relationship. It provides us with a pure quantitative measure. There are four main types of correlation: positive and negative, simple and multiple, partial and total, and linear and non-linear. The degree of correlation is measured by the coefficient of correlation, which ranges between -1 and +1. Correlation between two sets of figures can be studied by either drawing graph of that data, or by constructing a scatter diagram, or by calculating the correlation coefficient. Pearson's correlation coefficient is a measure of the strength of association between the two variables, whereas rank correlation coefficient is used for qualitative data when the data can be ranked. Regression analysis is used to predict the value of a dependent variable based on the value of at least one independent variable. The standard error measures the accuracy of the estimated figures when the regression line is fitted. Hope this module has given you a good understanding of the statistical concepts of standard deviation, correlation, and linear regression. Thank you.